SwayamPrabha. Digital India. Educated India.
Hello. In this lecture, I am going to continue the discussion on the phenomena that we observe on the rotating earth. As we have seen already that earth being a rotating frame sets up cyclonic circulation, that is what we have discussed in the last lecture. In this lecture, we are going to study the motion of particles that are thrown up from the surface of the earth. Suppose I can throw a particle vertically up, how does it drift because of the rotation of the earth? The drift that we as an observer on the earth see or feel or measure. The second thing that I am going to discuss is the Foucault pendulum, which was actually used to demonstrate that the earth really spins about an axis. We have already calculated the angular speed of the earth. It is 7.27 in 10 to the power minus 5 radian per second, extremely small, but it can show up in very large phenomena, and some of them are very destructive. Here we are going to look at a particle, the effect on a particle which is thrown up. We imagine a point at a latitude phi on the surface of the earth where we are doing this experiment. The experiment is throwing a particle vertically up at this location at the latitude phi. I again take this plane which is tangent to that point, tangent to the earth at that point, and set up a coordinate system, x in the east, y to the north, and z is vertically upwards from the center. Imagine a particle being launched vertically upwards, and here I will neglect the effect of air, etc. Imagine the particle is at currently a location indicated by this position vector r, which is represented in the local frame, the xyz frame, which is rotating, which is x I cap plus y j cap plus z k cap. Currently the particle is at that location and has a velocity, relative velocity, which means this is the velocity that we measure on earth. We will represent the velocity as seen by the inertial observer a little later. So, the relative velocity is x dot I cap plus y dot j cap plus z dot k cap as measured by us on the earth. Now, what is the acceleration the inertial observer will see for this particle? This is the most general expression. Now, here we have this omega of our frame, which has to be also represented in this xyz coordinate system. This is represented as this capital omega is omega of the earth, sin phi k cap plus omega cos phi j cap. You see, this is our omega direction, vertically up, and this is the angle phi, the latitude angle phi. Therefore, omega of the earth sin phi in the k cap direction and cos phi in the j cap direction. Acceleration of point O, now this center of this plane, center of the plane which is O, where the observer is fixed, where we are there, we are measuring the or observing this particle. the acceleration of this point is the acceleration of the center of the earth AG plus omega cross GO, this vector. This is the vector GO. Acceleration of the center of the earth because of its rotation about the sun, and omega cross GO, this is because of the spin of the earth. And what we will do is, we are going to drop that acceleration of the center of the earth moving around the sun. We will drop that. We are going to only consider the spin, the acceleration of O because of the spin of the earth, as if g is fixed. Now, if you use all these expressions in the acceleration of the particle, inertial acceleration of the particle, then you will get this very complicated expression. But this is straightforward algebra. You have to just plug in these values that are expressions, and you will get this expression of acceleration of the particle, inertial acceleration of the particle. This is the expression. Now, here we are going to again make these simplifications, that omega of the earth is very small, 10 to the power minus 5 or 7 into 10 to the power minus 5, it is like 10 to the power minus 4 radian per second. Therefore, we can drop omega square. Suppose we drop omega square and then we look at the acceleration, then it simplifies a little bit, and this is the expression of acceleration when you neglect omega square terms. Now, the kinematics is all done. We will move to the equation of motion of the particle. Mass of the particle is equal to the summation of all forces on the particle. Now, summation of all forces, air drag, etc., we are neglecting. The only force that acts on the particle when it is moving in air is the weight, and that too in the negative k cap direction. So, negative z direction. Here one more thing I must point out, this is an assumption that this particle is not moving far away from the point of launch, because otherwise its direction of gravity will change in this coordinate system. We are considering this flat earth approximation and the effect of rotation. Therefore, we consider that gravity is always vertically downwards at that location or nearby that location. Okay. This is our expression of inertial acceleration of the particle, and if I just substitute this and look at the I cap equation, j cap equation and k cap equation, this is our I cap equation, this is our j cap equation, this is our k cap equation, then we obtain these equations of motion, the coordinates, equations of motion of the coordinates as measured by the observer at the origin fixed to the earth. These equations will decide the motion of the particle. Now, these are 3 second order ordinary differential equations. We will need initial conditions. What are the initial conditions? At time t equal to 0, when that means at the point of launch, at the time this particle is launched, x equals to 0, y equal to 0, z equal to 0. So, it is at the origin of the coordinate system. X dot and y dot, the velocities, the particle is being launched vertically upwards. Therefore, x dot and y dot are 0. These are relative velocities, remember, and z dot is v z. This is the initial velocity of launch. So, these are my equations of motion and the initial conditions. I have to integrate. Now, if I integrate equations 2 and 3 and substitute in 1, what am I doing? In 1 I need y dot and z dot. What I do is I integrate these 2 equations once with respect to time, and that can be integrated because I have this phi as constant, omega, these things are all constants. Therefore, I can easily integrate equations 2 and 3 and obtain these integrals using the initial conditions. Remember, we have to always use initial conditions, and you can check that at t equal to 0, when x is 0, z dot is v z, and when x is 0, that means at the origin y dot is 0. Now, I substitute these expressions of y dot and z dot in the first equation, and once again neglect omega square. If I do that, I obtain this expression of x double dot, which I can integrate. I can integrate using the initial conditions to obtain this expression of x. This tells me how the x coordinate of the particle changes. Now, you will find that at t equal to 0, x was 0, but as t progresses, the x coordinate will change. This is quite surprising, and this happens because of the rotation of the earth, because if you put the spin of the earth omega as 0, there is no change in x coordinate, because we have thrown the particle vertically up. And if you substitute this expression of x, now in this expression of y dot, you will find only omega square. I mean, you will have this term, whatever you get will have omega square. Therefore, y dot actually hardly changes, it changes to very small order, order of omega square. Already omega is 10 to the power minus 5, so it is order 10 to the power minus 10. So, that is quite negligible. Now, substituting this in z dot, now this also can be substituted here in the z dot expression, and again neglecting omega square terms, you will finally get, this is quite surprising, that z dot follows the same dynamics as as we normally use for projectile motion. The correction comes in omega square. Therefore, our z, the motion of the particle in the vertical direction follows our usual expression, which is initial velocity times t minus half g t square. But what is now interesting, the new information that has emerged is this, that x coordinate is changing, which means the particle is going to move either east or west. I mean, that depends on this expression. Let us see that. By the way, the time of flight can be determined easily from this. So, z goes from 0 to 0. So, if I put z equal to 0, I will get 2 times, one is t equal to 0. So, initially z is 0, and then when it again comes back to the ground on the plane, when z is 0, that is the time of flight, 2 v z divided by g. So, these are the so the coordinate, the x coordinate of the particle is given by this expression which we have found, and just let us substitute T f into this expression of x. That means, after the full time of flight, where does the particle land? We have already noted that it is going to have a shift in the x coordinate, that means in the east or west directions. To find that where it will land up, I just put T f, I just substitute this expression of T f here, and I get this simplified expression of x at T f. That means, when I catch the particle, it would have shifted to the west, because you can check that x axis is towards the east. Therefore, if you get a negative quantity, it is going to be westward shift. You will also notice that this comes with cosine phi, phi is the latitude. Therefore, if you throw the particle, now phi in the northern hemisphere is positive, in the southern hemisphere it is negative. but cos phi does not change sign. Therefore, whether you project the particle in the northern hemisphere or in the southern hemisphere, the shift will be westwards. Next, we come to this very interesting pendulum which goes by the name Foucault pendulum after Jean Bernard Léon Foucault. The period is 1819 to 1868, not a very long life, but he was the first person to demonstrate the effect of rotation of earth. Through an experiment, he demonstrated that the earth spins. This was done in 1851. What is the Foucault pendulum? What did Foucault do? He hung a very long pendulum from the Pantheon in Paris, and he set that pendulum in motion. I have drawn approximately what happens with the same flat earth approximation, this plane which is tangent to the earth, and somewhere on the z axis this pendulum is suspended and it is oscillating. And here I have also drawn this a closer view of the pendulum. It is oscillating along a certain direction which bears a certain angle with the east. We will call this line of motion as the line which we can project the particle, the pendulum point mass. If you project it vertically downwards onto this plane, then the locus of all these points is the line of motion. Well, I have marked it line in quotes because, as we will see very soon, this is not a line. This seems like a line. Whenever you make a pendulum oscillate, it seems that it is oscillating in a plane, but if you wait long enough, then you will see something surprising if you can make the pendulum keep oscillating for long enough. And that is what we are going to analyze here. The expression of acceleration, now this we had derived, this is the acceleration, same acceleration for a particle at x, y, z, arbitrary velocity and acceleration. This is the acceleration as seen by the inertial observer. Now, here we will make the simplifying assumption that because this pendulum is very long, the z coordinate is not changing, because this is almost straight. Z coordinate is not changing appreciably, which means these variations of x and y with respect to the length of the pendulum is much smaller than 1. This we had considered also. We had simplified the pendulum equation. When we discussed the pendulum equation, we had used this simplification to simplify the equation of motion of the pendulum. Now, if you make this assumption that z dot is almost 0, z double dot is almost 0, almost it is like moving in a straight line, small amplitude motions, then the x and y, which now are the relevant equations of motion, they simplify to this form. Here, because of the rotation of the earth, we have these two extra terms now in the equation of motion. Otherwise, the first term and the third term, these are the standard terms that we normally come across in the equation of motion of a pendulum, which we also derived when we discussed the pendulum. Because of the rotation of the earth, we have these additional terms. Now, let us see what effect does it have. So, these are the two equations of motion. Let me define xi as x plus iy. This is a complex representation of x and y. So, xi is a complex number which is x plus iy, x coordinate plus I times y coordinate, I is under root minus 1. Why do I use this? Because I can then represent these two equations in a very simple form, but in the complex plane. How? X double dot and y double dot, just imagine that you are multiplying this by I is under root minus 1, and you are adding it to the first equation. Multiply the second equation by I and add to the first equation, then you will find this is xi double dot. This is, here you have y dot in the x equation, you have y dot in the y equation of x dot. That can be done by putting an extra I here, 2I omega sin phi xi dot plus omega n square xi. So, this just simply gives me xi, where omega n square is g over L, the standard definition. This was the key step that I use that extra I to generate these terms. In the x equation I generate minus y dot, and in the y equation I generate plus x dot. That you can very easily check, this plain algebraic step. So, this is our complex, I mean equation of motion in the complex plane. Coefficients are also complex, right. Let us assume a solution as is standard. So, this is a second order ordinary differential equation, but in a complex plane. We will follow the similar approach as used for ordinary differential equations. We assume this exponential solution with some unknown lambda and amplitude A. So, lambda should work for frequency. Okay. If I substitute this solution for xi, then I obtain xi square. If you take derivative, so xi dot is I lambda A e to the power I lambda t, and similarly you can find out xi double dot as minus lambda square A e to the power I lambda t. So, that is xi double dot, and once you substitute these things in here, you will obtain minus lambda square minus 2 omega sin phi lambda plus omega n square multiplied by A e to the power I lambda t is equals to 0. Now, A is not 0, then we are looking at the trivial solution if A is 0, and e to the power I lambda t will never be 0. Therefore, the only way this can be 0 is when this is 0. This is our characteristic equation. This is a quadratic equation. We solve for lambda, and we again drop capital omega square, the spin of the earth. We make some approximations and come to this expression. This is the expression of lambda. You get minus omega of the earth sin phi plus or minus omega n, which is the frequency of the circular frequency for the pendulum. Now, with this expression of lambda, we are going to substitute back. There are two solutions. We are going to substitute back in the expression of xi and write down the most general solution like this. A and B are arbitrary constants, complex in general. Therefore, you have this as your solution. Here you will notice that because this plus minus lambda which has come in, you have, because it will be superposition of these two solutions. What are the two solutions? E to the power I lambda 1 t with, let us say, lambda plus t, and e to the power I lambda minus t, that means lambda taken with the negative sign and lambda taken with the positive sign. So, a general superposition of these two solutions is a solution, and in lambda plus and lambda minus, this part is common, minus omega sin phi. So, that comes out as common and rest of it goes in the brackets. So, that is the superposition. Now, if you think about it, then the final solution of xi has this structure. It has a multiplying exponential, I mean see, this is what is the new thing that has emerged. This term is the new thing that has emerged, that involves the rotation of the earth. Now, if you put rotation of the earth as 0, then it gives us the standard solution that is oscillating with frequency omega n and phase psi. So, that is the standard solution of the pendulum, but because of this additional term, now you have something interesting. This is our solution, and remember xi is x plus iy. If you look at the real and imaginary parts, then this is what you have. Real part which goes with x has cosine of this argument omega sin phi t, and y is minus a sin omega sin phi t times that cosine term, normal pendulum oscillation. This is how x and y changes. Now, if you put once again, if you put that spin as 0, then you will see that the pendulum is oscillating like a normal pendulum that we write the solution. But now, with this additional multiplying factors which is dependent on the rotation of the earth, you can find out this line, what I was calling the line of motion, that slope of the line in the xy plane is y over x, which is tan gamma. I have marked tan gamma here. These two factors are common, a is also common. Therefore, what I am left with y over x, which is tan gamma, is minus of tan omega sin phi t, which means what? This gamma is a function of time. Gamma is a function of time. So, you should be able to find out what is gamma. From here we can find out gamma, and it turns out that gamma is minus omega sin phi t, straightforward. Therefore, this what we are calling line of motion is no longer a line, but its slope is gradually changing with time there, and you can find out that rate of change of that slope. It is minus omega sin phi, and remember, this is nothing but the rotation of the earth at that location perpendicular to the plane. This rotation is therefore, you see, this comes with a negative sign, which means that if you look from the top, this rotation is clockwise. I have shown this here. Gamma dot is negative, therefore, this rotation is clockwise as seen from the top, and this is in the northern hemisphere. It is where phi is positive. In the northern hemisphere, phi is positive, therefore, your direction of rotation is clockwise, whereas in the southern hemisphere, phi is negative, therefore, the rotation becomes counterclockwise as seen from the top. Now, this phenomenon was demonstrated by Foucault, and that clearly showed that the earth rotates, because this rotation of the line of motion is dependent on the rotation of the earth. And because this rotation of earth is very slow, and phi, see, on the equator this will not rotate. On the equator phi is 0, so you will have no rotation, but as you go northwards and at the pole this is going to the maximum, which is exactly the rotation of the earth, spin of the earth, that is the rate of rotation. Now, because this is small, if you have to demonstrate this, first of all you will have to take a pendulum which can oscillate long enough, because this rotation is very small. So, it will take a huge amount of time to see a sizable rotation, a perceptible rotation. Therefore, you have to power this pendulum, you have to provide power to this pendulum, so that it does not lose energy because of air damping and various other things. Normally all systems have damping, big or small, and you have to overcome this damping and make this pendulum oscillate for a long time, and then you can see this plane of the pendulum rotating. And this phenomenon, this system can also be used to understand how, for example, water in a sink, suppose you have a huge sink and you open the drain hole of the sink, how water will circulate as it rushes towards the center. So, that is also something like the cyclonic circulation. So, all these phenomena take place because of the rotation of the earth, which is very small, but has sizable effects or observable effects. So, to summarize, we have looked at certain phenomena that depend or that shows us that the earth is a rotating frame, and in certain ways we or in certain situations we cannot neglect that. We have looked at two examples. One is drift of a particle when it is thrown vertically upwards. You can try various other things like throwing it like a projectile at a certain location, and you can find out by how much distance this particle will miss the target, and this is an important problem for ballistics and for also for ICBMs, for example. Then we had finally looked at the dynamics of a Foucault pendulum, which clearly shows that the earth rotates. With that, I will close this lecture.